minus by 0.02 divided by 2. Right? To get 10 is 20 divided by 2. Okay? So this will be equal to 0.035 minus by 0.01 times by 0.02 times by 0.16. So it's equal to 80. So I get 80 times 10 to the power minus 6. Okay, now let me check. Yeah, I think I'm correct. Meter cube. Okay, so the width is 0.16. Let me do it again. Times by 0.02 times by 0.035 minus by 0.02 divided by 2 close bracket is 80 times 10 to the power minus 6 meter cube. Okay, good news. We have this, we have this, we have this. What is the thickness? Right? So we know the thickness is also parallel to the what? Right? This is also known as your thickness. So at point A, should you take thickness equal to 0.16 meters? Or should you take twice of 0.02? Which one will you take? Anyone. So this is equal to 0.04 meter.
The second option.
Yeah. You will take the smaller value. Smaller value, higher what? Stress. Right? The second value has higher stress. Right? You take the first value, when you divide by a big number, your stresses are lower. Okay? So from here, it's done. Okay? So the shear stress at point A is equal, so the V is 90 times 10 to the power 3. The Q is 80 times 10 to the power minus 6. The I can't remember. I is equal to 5.813. And then the thickness, because the thickness is with the left and right, is equal to 0.04. So this is equal to 90 power 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 0.04. It is equal to 30. Okay, 30.965 times 10 to the power 6 Pascal. Okay, that is the shear stress at point A. Then the next one we're going to do is we're going to find the shear stress at point B. Okay, so I'm going to go back to here. I'm going to take the diagram again. We're going to find the shear stress at point B. Okay, now we also know the centroid. Right, we are aware where the centroid is. Oi. Yeah. Are you all seeing a delay? No, right? Okay. So we know the distance from here to here is 35 millimeters. So now we want to find the shear stress at point B. So shear stress at point B, right? Point B is also equal to Vy over Izz Qz divided by T. Right? So now we look at this, we say, oh, okay. So Rule number one, right? We apply rule number. So Vy at point B, Vy is still equal to 90 times 10 to the power 3. Izz is equal to I think we can't remember now. 5.813. Right? Then the thickness is straightforward this time. It is because you have your variable your slider stop here, right? So your thickness is y bar. Your thickness is equal to twice 0.02. Okay, so thickness is equal to 0.04 meter. This is the next is what area do you take? Okay, so rule number one, V and I are constant. Rule number two, this is the datum. Rule number three, the analysis starts from where? From Y max. So this is the analysis direction. And rule number four, it cannot cross the datum, right? The second moment. So when that's the case, the area you have to consider is this area. Okay, no doubt, right? Vy is coming from here. Okay, so when this is the case, we are going to find our QZ. Okay, which is equal to width times depth multiplied by y bar. Okay, so we have to take twice the width. Okay, 0.02. Why twice? Because you have the left and right. Okay, and then we have the depth. Okay, the depth is 0.03. And now we have to find y bar. So this is where y bar is. Okay, and you have to be careful. The entire length, I click, the entire length is equal to 100. Okay, so y bar is equal to 100 minus by 35, or 0.1 minus by 0.035. Okay, and then minus by 0.03 divided by 2. Okay, then you have your y bar distance. Okay, so this represents your y bar. Okay, so this will be equal to 2, or 0.1 minus 0.0, 0.1 minus 0.035 minus 0.03 divided by 2, times by 0.03 times by 0.02 times by 2. So you get 60 times 10 to the power minus 6 meter cube. Let me do it again. So 0.1 minus by 0.035 minus by 0.03 divided by 2 equals 0.05 times by 0.03 times by 0.02 times by 2 is equal to 60. Okay. So from here, you're done. So the shear stress at point B is equal to 90 times 10 to the power 3. Okay. The QZ is 60 times 10 to the power minus 6. The cross-sectional area, the IZZ is equal to 5.813. Okay, 5.813 times 10 to the power minus 6. And then the thickness is equal to 0.04. So this is equal to 90 power 3 times by 60 power minus 6 divided by 5.813 power minus 6 divided by 0.04. It's equal to 23.224 times 10 to the power 6 Pascal. Okay. Okay. So the next thing we're going to do, right? Next thing I'm going to do. So what have we accomplished? Okay, we have accomplished finding the first moment of area, and shear at point A and point B. The last thing that we're going to do is we're going to derive. Okay, we're going to derive the shear stress distribution equation. Okay, so what the most important thing, okay, today, if I can get you all to understand how to find the first moment of area, second moment of area, okay, we are winner already. Okay, important things are the what you see that's critical. The 4 rules, right? The 4 rules over here, right? I equal to B and R constant, geometric data at the centroid, analysis start from y-axis, the first moment we cannot cross the centroid. These rules cannot be broken. If it is broken, right, what will go wrong is where your first moment of area will go stupid. Okay, when I say go stupid, it really goes stupid. Okay, now I want to go on to derive, okay, the distribution for the first for the shear stress. By deriving, I hope by deriving y'all can see where these rules are how these rules are developed. Okay, so it's important that I show you how the shear stress distribution equation. Okay, means we are working with variables now. Okay, I know we don't enjoy working with variables, but as an engineer, okay, listen, I'm training you guys to become engineers. I'm not training you guys to become technologists with a degree. No. Okay, once you finish this course, all of you will be engineers. Okay, I don't think so. He said no software in lecture 1. Can we use Excel? Okay, you can use Excel to check your answer, but you don't cut and you cannot just write your answer from Excel onto the page. Alec, does that make sense? Okay, you can use Excel to see your numbers are correct, but you still have to write down your working. I know if you program on Excel, in your final exam, you cannot just show me this. And then you cut and paste your Excel spreadsheet, your Excel, okay, your Excel. Okay, this I cannot give you mark, you'll get 0. Okay, Alec, that makes sense, right? Okay. Show steps. Yeah, you're absolutely right. You have to show your steps. Okay. So now, as I said, and I need another 15 minutes of your time, okay? Because I went to explain quiz 1, quiz 2, and also your, what is that? About your term test. Okay, so let's look into shear stress. Distribution. Okay. So the horizontal beam, so when we divide the beam this way, right, the horizontal part, this is what we call our flange. I want you all to learn these terms, okay? That is known as our flange. This is known as our web. Okay, I want you all to learn this term. What is a flange and what's a web? Okay. And then we are going to draw we know already where our centroid is, right? We know the distance from here to here is equal to 0.015, right? Sorry, I should write bigger. We know this distance is 0.015, and we also know the distance up to the maximum is 0.035 meters. Okay, one is. So we are going to write the shear stress distribution on the flange section. And the limits is 0.015 y, and it will the maximum